Good morning to one and all. First of all, I would like to thank for the given opportunity in front of you. I am Dhanabalan, going to present my topic spin orbit interaction, coupling scheme, and fine structure. Is from chapter 1 atomic spectra. First one, spin orbit interaction. Actually, an electron revolving in a Coulomb field of the nucleus finds itself in an internal magnetic field because in the frame of reference of the electron the nucleus revolves around it. The magnetic moment of the electron interacts with its internal field. The strength of the interaction depends on the direction of the magnetic field, which itself depends on the spin of the electron. Thus, the interaction is spin dependent and is framed as spin orbit interaction. Let us calculate the internal magnetic field. Consider an electron of charge minus E and mass m revolving around the nucleus of charge plus Ze with velocity v in circular orbit of radius r in the rest frame of the electron. We see the nucleus moving in a circular orbit of radius r in the direction opposite to that of the electron with a velocity v. This is equivalent a current loop with current I given by I equal to Ze by 2t equal to Ze by 2 pi r by v equal to Zev by 2 pi r. The magnetic field due to such a current loop is B int mu naught I by 2r equal to mu naught Zev by 4 pi r square. Here B int represents the integral magnetic field arising in the atom as explained above. In vector notation, B int equal to mu naught Ze r vector into v vector by 4 pi r square modulus r vector. B int equal to mu naught Ze by 4 pi m r cube into r vector into mv vector. B int equal to mu naught Ze by 4 pi m r cube L, because L equal to r cross mv, equal to Ze by 4 pi epsilon naught mc square r cube into L. It is usually mu equal to 1 by epsilon naught c square. Therefore, the spin orbit interaction energy is given by Em equal to minus mu s B int. We know already the B int represents that internal energy. Since we have assumed electron to be at rest and the nucleus to be moving, therefore the electron will have only one motion and is spin magnetic moment only. A dipole of moment mu vector s placed in a magnetic field of strength B vector interacts with it such that potential energy of dipole is given by Em equal to minus mu s vector B vector. Therefore, the spin orbit interaction energy is given by Em equal to minus mu vector s into B int. Mu s equal to minus gs mu b by h cross s vector. We know already B int discussed. Then Em equal to gs mu b by h cross s vector B int equal to gs mu b Ze by 4 pi epsilon naught mc square r cube h cross into s L vector equal to Z square 4 by epsilon naught m c square r cube s vector l vector. It is used mu b equal to e h cross by 2m and g is equal to 2. The interaction energy in a frame of reference where electron is moving and the nucleus is at rest becomes Em equal to Ze square by 4 pi epsilon naught mc square r cube sl vector. Next, Jj equal to j square equal to, we know j equal to L cross L plus S equal to L square plus S square plus L vector S vector plus SC vector into L vector. J square equal to L square plus S square plus 2S vector L vector. So S vector L vector equal to J square plus L square plus S square by 2. This topic over. That means next topic, coupling scheme. Coupling scheme means in an atom having 2 or more electrons, the orbital and spin angular momenta of all its electrons can be added together in 2 ways. The method of combination depends on the interaction or coupling between the orbital and spin angular momenta. 2 types of schemes have been developed. They are, first one LS coupling, second one JJ coupling. The LS coupling another one name for Russell's Sundar's name. First one LS coupling. The type of coupling which occurs most frequently is the LS coupling. In this type, all the orbital angular momentum vectors of the various electrons combined to form a result L and independently. All their spin angular momentum vector combine to form a resultant S, capital S. These resultant capital L and capital S then combine to form the total angular momentum J of the atom. Here figure also shows these representations. That means capital L equal to summation small li, capital S equal to summation small si. Similarly, J equal to capital L plus capital S. L is always an integer including 0. S is an integer for an even number of electrons and odd multiply of 1 by 2 for an odd number of electrons. Hence, J must be in integer, S is an integer and J must be odd multiple of 1 by 2 if S is odd number. It can be shown that when L greater than S, J can have 2S plus 1 values, and when L less than S, J can have 2L plus 1 values. In particular, if L equal to 0, J can have only one value, namely J equal to L. Yes. This is an electron scheme. Here present 2 electron, 3 electron and 4 electrons. We know already spin means there are 2 directions, spin up and spin down. Spin up means plus 1 by 2, spin down means minus 1 by 2. Just see here from 2 electron scheme, first one both electrons are positive, that means plus 1 by 2. So 1 by 2 plus 1 by 2 equal to call that 1. Then second, from second electron scheme, one is a upper direction, another is a down directions. Both are cancelled. So here 0. Similarly, for third 3 electron scheme, 3 electrons available. Both are all are in up directions. So 1 plus 1 by 2 plus 1 by 2 plus 1 by 2 is called 3 by 2. Then another section of 3 electron scheme, first 2 are upper directions, next one down directions. So 1 minus 1 by 2 is called that 1 by 2. Similarly for 4 electron scheme, and in 4 electron scheme, left side 4 electrons are available, all are upper directions, so plus 1 by 2 plus 1 by 2 plus 1 by 2 plus 1 by 2. Okay, here 2. The another 4 electron scheme, first 3 electrons are upper, next only one down, so 1 plus 1 by 2 plus 1 by 2 plus 1 by 2 minus 1 by 2 is called that 1. Then another one, first 2 electrons upper, second 2 electrons down, so all are cancelled, come to 0. So here present in 4 electron scheme, S equal to 2 comma 1 comma 0. Similarly 2 electrons present, S equal to 1 comma 0. 3 electron scheme, S equal to 3 by 2 comma 1 by 2, and 4 electron scheme, S equal to 2 comma 1 comma 0. The next one, JJ coupling scheme. This method is employed when the interaction between the spin and the orbital vectors of each electron is stronger than the interaction between either the spin vector or orbital vectors of the different electrons. The orbital and spin angular momenta of each electron in the atom are added to obtain the resultant angular momentum of the electron. That means the small j I vector equal to small li vector plus small si vector. The vector sum of all the individual small j vectors gives the total angular momentum capital J of the atom. Thus J equal to capital J equal to summation small ji. This type of coupling exists mainly in heavy atoms. Here figure shows also the JJ coupling directions. This topic over. Next topic, fine structure. In fine structure, 10 out of the 11 electrons of the normal sodium atom are interlocked in closed cells. They contribute nothing to the angular momentum of the atom. We have to consider only one state of 11th optical electron in discussion, the spectrum of neutral sodium. The spin orbit coupling gives rise to splitting in the spectra called fine structure. Here L equal to 1, S equal to 1 by 2. This is split up. We know already J equal to L plus S. So J equal to, for uppercase, J equal to 1 plus 1 by 2 is called 3 by 2. Similarly for negative directions, means minus 1 by 2, J equal to here plus 1 by 2. These will be split up for positive directions, Mj equal to plus or minus 1 by 2, comma plus or minus 3 by 2. For negative directions, Mj equal to plus or minus 1 by 2. The D line belongs to principal series. Lines of the principal series are due to transitions from P state to S state. For the upper P state, L equal to 1, J equal to L plus or minus S equal to 3 by 2 or 1 by 2. Hence, the two possible terms are 2P 3 by 2 and 2P 1 by 2. For the lower state, S state, L equal to 0, so J equal to 1 by 2 for positive terminal only. The selection rule delta J equal to 0, comma plus or minus 1 but not equal to 0 arises from conservation of angular momentum. The electrons can jump from one orbital to nearest another orbital level, another energy level, but cannot jump one to all other or jumping to another energy levels. For example, here S2P possible but cannot possibly S2D. Here the figure given the example of that energy transitions from one energy level state to another energy level state. This topic over. Next topic, Spectroscopic terms and selection rules. First one, the spectroscopic terms. The outermost electron in an atom or ion is the one that usually undergoes transitions, and so the state of the electron describes the state of the atom or ion. The configuration describes the n and l values for all the electrons in an atom. For example, the ground state of boron has a 1s square, 2s square, 2p configurations with 2 electrons filling the n equal to 1 level. Here L equal to 0. 2 electrons in the n equal to 2, L equal to 0's orbitals, and the fifth electrons having to populate the 2p orbital. The level of the set of 2j plus 1 states with specific values of L, S and J. The difference in the energy between two levels gives the wavelength or frequency of an atomic transitions. The term in the set of levels characterized by a specific S and L. The ground state of boron has a 2p 1 by 2 term. Closed cells always have a 1s0 term. Atoms whose outer electrons have L equal to 0, 1, 2, 3, 4 are referred to as S, P, D, F, G terms respectively. For example, in the ground state, boron has 4 electrons in 2 in the n equal to 1 level and n in the n equal to 2 level and 1 p electron. The ground state term of the atom is P. Warning, and the S in an S electron has nothing to do with the quantum number S, and this is a carryover from early spectroscopic nomenclature for alkyl atoms. Those with closed cell of electrons pulse a single valence electron, such as lithium, sodium, potassium, Mg2, calcium, calcium 2. Second one, free ion spectroscopy term for d n configurations. The electron repulsion causes a given electron repulsion causes a given electron configurations the terms energy level of atom or ions that arise due to inter-electronic repulsions. Here given configurations of D here. Similarly, repulsion Saunders terms. Here colors differentiated. The ground state terms are different color here mentioned. The D0, D1 for the first orbit 1s. D1, D9 he added 10 atoms. Second one, that means results the terms 2D. Then D2 small, D2, D8. Here next energy level 3F, 3P, 3G, 1D, 1S. Similarly for D3, D7, that terms 4F, 4P, 2H, 2G, 2F, 2D, 2D, 2P. Next one, D4, D6. He added 4 plus 6 equal to 10. Similar here, 5D, 3H, 3G, 3F, 3F, 3D, 3P, 3P, 1I, 1G, 1F, 1D, 1D, 1S, 1S. For D5 orbit, 6S, 4G, 4F, 4D, 4P, 2I, 2H, 2G, 2G, 2F, 2F, 2D, 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 2P, 2S. We will do the different orbital levels. Here mentioned again, I will repeat it now. The different colors are mentioned. It is that ground state terms. Next one, selection rules. In complex ions, there are an enormous number of possible transitions. Not all of these possible transitions are observed. This is because some transitions are more likely than others. Selection rules were arrived at empirically to describe those charges in quantum numbers that were observed is a permanent transitions, and those which did not is a forbidden transitions. The basic selection rules, which strictly apply only to simple configurations which obey strict LS coupling. The levels of L and S do not affect each other. This lack of interactions is known as LS coupling. In complex atoms or ions, levels of L and S can interact, leading to a breakdown in LS coupling. When this happens, L and S are no longer interpretable in terms of angular momenta, or delta equal to 0 plus or minus 1, delta L equal to 1, delta J equal to 0, plus or minus 1, except that J equal to 0, because J equal to 0 is forbidden. Next one, delta S equal to 0. Then delta M equal to 0, plus or minus 1, except the M equal to 0, J equal to 0 is forbidden if delta J equal to 0. As the atoms become more complex, strict LS coupling fails to hold, and these selection effects become weaker. Perimeter lines are those whose transitions probability is high. Here given the perimeter transition lines, P branch, Q branch and R branch. These transitions are also based on that selection rules. The energy cannot jump from one to all another energy levels, only jump nearly energy levels. This principle based here explained that 3 type of branches. This topic over. Thank you for watching and visiting. Thank you.